So good afternoon everyone. Today we are going to study the equations of equilibrium. So in last class we studied about the nomenclature, sign convention and the forces acting on a small particle or small area surface and the stress tensor is also explained. In this we studied that normal to this plane a normal stress is acting and tangential to that plane there will be tangential stress is also acting. So coming to the equation of equilibrium derivation, we are considering a small cubical element of area dx into dy and of volume dx, dy and dz. That is, next direction we are considering from one plane to another plane of distance dx, and in y plane we are considering from one plane to another plane dy, and in z direction we are considering from one plane to another plane dz. So these are the distances of this cubical element. So these all are in the x, y and z direction or axis, and we are considering that it is a continuum body subjected to the stress components system. And we are also considering a body force. That is, in the last class we explained that in body force, what is body force? Body force means the force which is acting on the or acting on entire volume, like for example, like gravitational force. So this is also considering during this proof. So first of all, we are considering this mass in a equilibrium condition. So what is our equilibrium condition equation? That is sigma x equal to 0, sigma y equal to 0 and sigma z equal to 0. If a body is in equilibrium, we always start our analyze with this condition, that is the forces acting on this xyz axis is the sum of forces acting on this xyz axis equal to 0. Thus this volume will be in equilibrium. So we are considering here we are considering this portion. So I can call it as A, B, C, D plane and E, F, G, H. So here in this A, B, C, D plane, that is this plane. Okay, A, B, C, D plane. In this plane, the normal stress is considered as sigma x. Then this tangential stresses or shear stresses is considered as x, z and tau x, y. So here you can see in the last class we explained the plane that is perpendicular to this axis. That is in this axis, x-axis, we are analyzing this as x plane, or we can also denote it as a y-z plane. Either we can say this is a x plane or we can say this is a YZ plane. Both are using. So I am notating as this is X plane. So behind that this is also perpendicular to X axis. So this is also an X plane. So considering that the normal stress acting is sigma X and the shear stress acting is first in the nomenclature we studied the first letter denotes the plane which is acting and the second denotes the direction of its action. So here considering sigma x, tau xy and tau xz, and after that we are moving to this plane, that is EFGH plane. In this plane you can understand that there is a distance dx is considered. So that displacement factor is also considering when we write this stress factors on this plane, EFGH plane. So here sigma x, here the distance is dx. So we can say this stress on this area as sigma x plus then this displacement component, that is dou sigma x by dou x into dx. So stress and the variation on stress according to the displacement dx. Here also the same is followed, that is tau xy, that is opposite to that system, tau xy, dou by dou x with respect to x, tau xy into dx. Similar to that, we can say tau xz is tau xz, dou by dou x of tau xz into dx. Okay, so this is the stress vectors we can say on this plane and this plane, and this plane. Okay, the next one, so we consider the both x planes. Both this x planes. Let's say this is first plane. This is also the x plane x1, x1, x2. Both two x planes is considered. In the next case, what we are considering is this B, F, G, C. Also A, E, H, D. Okay. So here this plane is perpendicular to which plane, which axis, that is z axis. So we can say that either it can be explained as z plane, or we can say that xy plane, or we can call as xy plane. So in z plane, similar to this previous explanation, here the normal stress is sigma z, and the shear stress acting is tau x, tau z x, that is in the x direction, and tau z y in the y direction. Coming to this distance, we know there is a distance dz is given. So here is also we considering the tau zx plus displacement factor dou tau zx by dou z into dz. And similar to in y direction, we can say that dou zy plus dou by dou z of dou zy dz. And here sigma z, here coming after dz distance, we can say that sigma z plus dou by dz, sigma z dz. So we consider a z1 and z2 plane, that is we consider x planes as well as z plane. So the remaining is y plane. So y plane means D, H, G, C. That is y axis is perpendicular to this plane, this plane as well as this plane. So this is what we are going to consider. Okay. So here what will be the values, that is sigma y is the normal stress, then tau yz. The y plane is z direction. Here tau yx, y plane x direction. So after a variation of dy distance, what will be the values of stresses on this dcgh? Stresses will be here sigma y. After dy distance, we should take the displacement component, that is sigma y plus dou by dou y of sigma y into dy. And coming to this tau yx x stress, shear stress, here tau yx plus dou by dou y of tau yx dy. So in every one plane is considered, and the next plane perpendicular, no, parallel to that will be having some distance. For example, this is x plane x1 and this is x2. Here the distance of dx is here. So when we write down this stress on this plane, we should consider the stress plus this displacement factor also. This is what we studied in our BTech. In every FM derivations, even in the essay derivations, we studied this kind of problems. The same thing is applied here. Okay. So initially what you need to do during this equilibrium equations derivation, you have to write down that we are considering a continuous body of equilibrium in equilibrium condition, and then you draw this figure in a very neat manner. You can either use different colors of pen, and then you can notate these stress factors. First you have to notate the stress factor of one plane, then you should consider the next distance between that and write down the next plane. After that you consider another plane. If I am taking this y plane, then you will consider the distance and write down the next plane, and consider the other plane and write down the next plane. So thus the first part is over. So the main thing happening is that we will confuse if we didn't understand which all stresses is coming, that we need to know that the axis perpendicular to the plane will be known by that axis name. That is, here x axis is perpendicular to this plane, so we can say that x plane, or sometimes x plane is also known by the yz plane, bicep plane. But this is more convenient to use. That's why I'm using the name X plane. Either we can say X plane or bicep plane, or here you can say this is Y plane, or you can say Y plane, or you can say X Z plane. So similar to that, you have to mark all the stress components here. Then the next job is very simple, that I already mentioned. For equilibrium condition, you have to take sigma x equal to 0, sigma y equal to 0, or sigma z equal to 0. That's the three equilibrium condition that we usually follow. So here, first one is sigma x equal to 0. Okay. First, we have to consider the equilibrium condition in the x-axis direction, that is sigma x equal to 0. So you should consider the first component, that is sigma x plus this value is in the direction of x, also this value is there. Another x direction is tau yx is here, also this the horizontal axis, you should consider the horizontal axis, and here comes this value and this value. Okay, so when you write sigma x plus sigma x by sigma x dx, dou x into dx. So first factor is this, and minus sigma x. Then you are considering, if it is x-axis, you have to consider the area of this, means here that this distance is dy, here the distance is dz. So the area will be dy into dz. So first write down the stress component, and the area is dy into dz. Sigma x dou by sigma x minus sigma x dy dz. Similar to that, you should consider the next one, that is tau yx plus dou by dou y of tau yx into dy minus tau yx into the plane in which it is acting, that is dz as well as dx. So this write down here, and the next is which one? We consider this. Consider this. Which one we need to consider? Z. Okay. Tau is zx plus dou by dou z of tau z into dz minus tau zx. So this also we need to consider. This is tau yx here, tau yx dou by dou y of tau yx dy, also tau yx. So what how many of you need to consider? First, you need to consider sigma x equal to 0, that is in the x direction. You should consider the x direction factor. So one is this, another one is this, and the area acting is dy into dz. Another is this, and the x direction this. The area which it is acting is dx and dz, right? This portion, this area it is acting. Another one is, so this consider, and this values. So this one and this one, and the area which is acting is dy and dx. Okay, I hope that's clear. So you consider, and we in this proof, we initially told that we considering the body force. The body force Fx is acting on this entire volume. So we are considering Fx dx dy dz, and the according to the equilibrium condition sigma x equal to 0 is we are equating to 0. Then simplify this thing. So here sigma x and sigma x gets cancelled. Here also it gets cancelled. So writing down dou by dou x of sigma x dx dy dz, dx dy dz. Then the another fact is dou by dou y of tau x dy dx dz. Then dou by dou z of tau zx dx dy dz. Then the next one is fx. Here it is z. Here it is. This is marked as z. Okay, that is dou by dou z of tau zx into dz, dou x dou y. So write down all these things. Here dou x dx by dy dx dy dz is common. Taking in that on outside and equating to 0, we will get the equilibrium equation on the x direction. That is dou by dou x of sigma x plus dou by dou y of tau yx, dou by dou z of tau zx, and fx. Sometimes mostly in the case we didn't consider this fx in problems, and also that time you can put this fx equal to 0. So similar to this, we have to write the sigma y equal to 0 condition. From this figure you can see that how we'll start analyze sigma y equal to 0. So when we considering sigma y equal to 0, we need to consider this, we need to consider this, we need to consider the y direction factors. Here it is, here this, here this, anything that 1, 2, 3, 4, 5, 6. So these are what we need to consider. Similar to that, first you have to write sigma y equal to 0, sigma y equal to 0. First one is tau xy plus dou by dou x, tau yx dx minus tau xy. And the area which it is acting is, this is dx and this is dy. So into dx dy. Another one is, the next one is, first we consider this green markings, and we are going to consider this red marking, that is sigma y is there. So first sigma y plus dou by dou y of sigma y dy minus sigma y into the area which it is acting, that is dz into dx. So the next group is the z direction. So here dou z by plus dou by dou z of dz sigma z dz, and the this minus sigma z. So area which it is acting is dy to dx. Okay. So similarly, you can write down this thing and taking dy dx and dz on the outside, we will get similar to that. We will get dou by dou x of dou xy plus dou by dou y of sigma y plus dou by dou z of dou zy plus fy. Fy is the body force acting. It is also on the entire volume. That then we will take dx dy dz. Volume is taken. Okay. So in z direction, similar to that, you have to put the sigma z equal to 0, take the z component and write down. Similar way, you will get this equation. So you need to study these three equations. That is equilibrium equation in the x, y and z direction. Okay. So if when body forces are absent, then we can write this fx equal to 0, fy equal to 0 and fz equal to 0. So we have the equation as the last time is not taking and the three equations will be like this. Okay. So this I will explain the next class, that is another symmetrical portions, because before this topic I write down that in the above section, that's why. So this will be explained on the next class. This is not related to this book. Okay. So we need to express in this TOE or theory of elasticity and plasticity. Mostly we express in the matrix format. So from this equation, I know most of you know this, right? So you have to write in the matrix form. I will explain if anyone don't know. That is, you first write down this sigma x, sigma y, sigma z, z, another tau xy, tau yz, and tau zx. Okay. From this proof above that, we will get that tau xy and tau yx is similar. That's why we are not writing all these terms. That is, here tau yx is coming, here tau xy is coming. So we are not writing tau xy then tau yx and all, because this is proven as similar. In your MOS also you studied that. I hope you know this figure, right? This figure tau xy, tau yx. So for equilibrium, both equal values and opposite direction, this will get cancelled here to make this body equilibrium. That's how this proof is going. So we know that tau xy equal to tau yx, tau yz equal to 2z by tau xz equal to tau zx. That is from your previous BTech knowledge and all. Otherwise, you have to do this tau xz equal to tau z by zx proof, the similarity proof, that will be given as homework in future. Okay. So what we discussed is that we got this final answer. We got this final answer, or the three equations we got. So what we need to is find is that we have to write down in the matrix format. So how you write down in the matrix format? That is here. That we are writing sigma x, sigma y, sigma z, tau x by tau y, z, tau zx. So here these terms are writing on the one matrix, one column matrix. Okay. Then we are writing these terms on that. So if fx, fy, fz is taking, we need to write this plus these three fx, fy, fz in the column matrix. That's given here. So here this is equal to 0. You can see here the equality is on these three equations. It is 0. Okay. So write down that. So first is sigma xx. So you can write down dou by dou x. So dou by dou x into sigma xx, right? Dou by dou x into sigma xx. The next one is sigma yy. So we in the first equation we don't have a sigma yy term. So put that as 0. The another one is sigma z. In the first equation, no sigma z. So put that there also 0. The next one is tau xy. Here I explain tau xy and tau yx is similar. So for tau yx or tau xy, what is the coefficient? That is dou by dou y. We are writing dou by dou y here. The next one is tau yz. So no tau yz term is here. So put there as 0. The next one is tau zx. So here given as tau zx. So the coefficient is dou by dou z. So dou by dou z into dou zx is getting. So next term is sigma xx. In the second equation, no sigma xx, put there 0. And sigma yy, is there any sigma yy? Yes, sigma yy is here. The coefficient is dou by dou y. Put it here. Sigma z term is not here, 0. Then the next one is tau xy. The first term is tau xy. That coefficient is dou by dou x. Put there, dou by dou x. Then tau yz. Tau yz, here tau zy is here. Both are similar. So coefficient of dou by dou z is given. Dou by dou z is given here. The last term is tau zx, which is not in this equation. So put there also 0. Similar to that, write down the last term also. Here sigma xx equal to 0, sigma yy equal to 0, but sigma z is here. So dou by dou is z. Then tau xy. Is there any tau xy term is here? No. So put there 0. Then tau yz. Tau yz is here. The coefficient is dou by dou y. Put it here. Tau zx, yes. Dou by dou x, put it here. So we can write down the equation in the matrix format. So here, so after multiplying this into this, we will get up to this answer. If the body force is considering Fx, we need to add Fx. That is given here, Fx, Fy and Fz, which is equal to 0. So this is the equation of equilibrium. This is the equation of equilibrium. So what you need to do is that first you write down the theory like equation of equilibrium. So we are considering this thing and continuous and rigid, or you should write the terms that it is having a length of dx, breadth of dy, height as dy and the breadth as dz, like that you have to write. Then you draw this figure. Draw this figure in a larger size. Otherwise, you can't put all these stress vectors on this figure. So first draw this figure, then mark down this mark down this stress factors. Okay. So if we considering one plane and the next plane, we have to consider the distance or the displacement component also. You know that thing, right? So first sigma x plus this factor also here. So in the shear stress also we have to put like that. So after that, our aim is to make the equilibrium condition, that is sigma x equal to 0, sigma y equal to 0, sigma z equal to 0. So considering sigma x, if sigma x equal to 0 is the first consideration, then you have to find the x factors, x direction components, that is here this is one, and the area which it is acting, multiple the first this in area which it is acting, and the another vector, that is here this one and this one, and the area which it is acting, that is dx as well as dx as well as dz. So the next one you have to consider this one and this one and the area which it is acting. So after considering, and if body force is considering and body force is acting on the volume, so body force into the volume which it is acting, and simplifying that, common terms are cut and then the common terms are taken outside, and you will get the equilibrium equation in x direction as like this. And similar to this, you have to do sigma y equal to 0. In that, you have to consider the vertical components. Similar to this, you have to write down, and you will get the similar equation like this in y direction and in z direction. These three equations are very important. So you should study these three equations. Also, in this you have to write this in a matrix format. That's how here written as in matrix format. So this is all about equation of equilibrium, and this is also a university question. So this is also important. You should write down in a neat manner. Uh, Draw this figure in a large size with clear notations and clear stress factor. Stress factor should be write down in a clear manner. You can use different colors of pens for easy identification. And that's all for this class. Thank you all.